So now we come to the fourth talk of the session, to Dr. Marco Huber, Professor Dr. Marco Huber. He is a professor for cognitive production systems at the University of Stuttgart. He's also head of the Cyber Cognitive Intelligence Center at Fraunhofer EPA. Before, he has been chief consultant and data scientist, and also he was university teacher before at Karlsruhe, and before he studied in Karlsruhe and Sydney, Australia, I think, computer science. I hope I got this correct. So a warm welcome to Marco Huber, and we are very much looking forward to your talk.
Yeah. Thank you. So, thank you very much. Thanks for the introduction, and great to be here with you. I would like to speak about dependable AI and qualification of AI-based quality inspection systems at Fraunhofer IPA, which is located in Stuttgart. I'm responsible for the AI team, and we do a lot of quality control in manufacturing because our institute is heavily focusing on manufacturing engineering and production science. And quality control is a very typical topic. And beyond that, we are also concerned about how do we make AI systems, which are more and more involved in these quality control aspects, safe and dependable. That's the background of my presentation. Very briefly on the institute. We're located in Stuttgart, at still the heart of the German automotive industry, I would say. Even though it's challenging, we are headquartered in Stuttgart, but we also have subsidiaries in Mannheim, for instance, Bayreuth and other cities, where there are more than 1,200 employees. So we are one of the largest Fraunhofer institutes, and as I said, focus heavily on machinery, plant engineering, mechanical engineering, automotive industry, but also, for instance, in the health industries. All right, when it comes to AI, one of our key focuses, our research focuses, is on dependable AI system. We don't call it responsible AI or trustworthy because we are really speaking about technical systems, and dependability is the technical term that fits best here. And you will see, I have several topics here, and we will grow out of that during the course of my presentation. At the heart of our research are the three main topics: explainability, robustness, and uncertainty quantification. I think explainability, everybody knows what is meant by this term. We would like to understand on what basis an AI system, a machine learning model, is doing its decisions. Uncertainty quantification becomes a problem when we have a lot of noise in the data, or the model itself is noisy. And we have to ask the question how certain decisions of an AI model are, and can we quantify this uncertainty by the model? And robustness is about if we tweak the data, ideally we would like to see the following behavior. If we modify the input data slightly, also the output should change very slightly. We would like not to have big changes by just minor variations in the input data. And if this is not given, we do not have a robust model. The question is, how can we assess the robustness of a model? I have brought you two examples, one for explainability and one for robustness. Very recently, we published work on which is called RENT. RENT stands for Runtime Efficient Network to Tree Transformation. Actually, there was some paper some years ago which showed that artificial neural networks are decision trees, which was a bit surprising result. Because decision trees are usually termed as a white box model, while neural networks are black box model. But under certain mild assumptions, it can be easily shown that you can transform any neural network into a decision tree. Sounds good. The problem is this decision tree becomes very huge, and it's a multivariate one. So if you are not that familiar with decision trees, the most decision trees people know are univariate decision trees, meaning in each decision node you only make a decision based on a single feature. In multivariate decision trees, you make decisions by multiple features, which is a problem because you now have a linear decision function and you have many nodes, so it becomes a opaque model again. So not really helpful, so to say. And the second problem is this transformation, as it was proposed by some researchers some years ago, is really slow. It does not scale. And because this session is also about scaling, we found the result interesting, but not practical. So we reworked the whole approach. We fixed some proofs. There was errors in the proof by this method. We also extended it, and we significantly improved the computational efficiency. We speak about orders of magnitude. The details you can find in the paper. And we show, of course, again, we have this problem that the decision tree is not that helpful, but out of the decision tree, you can derive other methods, other measures that really help to understand the decision making. For instance, we can show that you can derive ground truth feature importance, the optimal feature importance, not the fake feature importance you get out of Lime or SHEP. It's really the ground truth feature importance, locally, globally, or region-wise. We call this rent FI, so rent feature importance. You can derive optimal local linearizations of the neural network. You can make counterfactual explanations. You can visualize areas in the input space which are leading to the same decision. And you can also use it for assessing the robustness. So the short notice is decision tree, nice, but not really helpful. But out of the decision tree, you can derive further measures, and these are really helpful. What you see on the pictures on the right-hand side is a comparison of the ground truth feature importance derived from rent compared on multiple data sets with other well-known techniques like Lime and SHEP many people are using. And ideally, all the columns should be very low. This would mean that they agree on the features. But as you can see, especially on the very right-hand side, you have a large plots here, which means that Lime and SHEP, for instance, which is brown and I think it's blue, deviate significantly from the ground truths. So they are just not useful, even though many people are using them. So the short notice is stop using Lime and SHEP, use something else, maybe rent feature importance. And this holds for local feature importance, meaning for individual decisions, but also holds for the global feature importance if you make global statements about which features are used. All the details you can find, we have to put the paper on archive. It's a quite lengthy one because a lot of mathematical proofs, but I think it's worthwhile to look into it. We also provide the implementation if you would like to test it out. About robustness. Robustness, as I said, is the question if you deviate or modify the input features slightly, maybe in a classification problem, you would like to see that the classification just not changes. Because maybe you have some noise on the image, this should not affect the classification. But we observe different behavior on many machine learning models. You can make a statement, a statistical statement about robustness. This you can see here. What you would like to see if you apply a transformation on the input, you would not like to see switching the classes by a high probability. This can be then transformed into a statistical proof, and then based on a confidence level, you can statistically prove whether your method is robust or not. The nice thing about this statistical test, it's model agnostic. You can apply to any machine learning model, and you do not need to have ground truth labels. It's label free. And on the plots, you can see some examples. You see these images of a dog. And in each row, you put different kind of perturbations like noise, dirt, or we clipped removed some pixels on the right-hand side. Then you can see by the intensity you put this kind of perturbations on the data, how the global robustness is assessed by our test. And this test method can also be applied by very well-known local verification methods, which are in the state of the art. And if you combine them, you can improve these existing local verification models in addition. Also here, papers, you can find it online. So these are the kind of really methods we work on. We are working on methods which help people in understanding, testing their models. But we are doing more. We also would like, so in this phase, oftentimes it's already too late. Yeah, you build your model, and then you realize it's a black box, it is not robust, and then you have to rethink. Ideally, you should do these kind of considerations early in the development process. So we are thinking about AI engineering. How should AI models, especially robust and safe AI models, be built from the beginning? This is what we call AI engineering. How do we do the AI development right? Here we also provide some methods, some means, and also some procedures to support the development of machine learning models. One example you can find here, together with some industry partners, we extended some well-known technique which are called model cards. You probably know them. If you interact, for instance, with Hugging Face, you know these kind of model cards. There are also already in the state-of-the-art data cards, so also you write in metadata on the data itself. We extended it because machine learning applications is not only about data and models, also about actually a use case you would like to solve. And at some point in time, hopefully, you would like to deploy the model. And also there you have certain requirements that need to be addressed. So we extended it by use case cards and operationalization cards. And we also took in consideration which aspects of the AI Act and other regulations need to be considered in all these phases. So it is a means, more like a checklist, that supports AI engineers during the development of an AI model. Also here, you can find a publication with all the details on arXiv. We use this technique, for instance, in a nice project. I like this very much. So if you are a coffee one who likes coffee, this might interest you. There was a project together with BKI and DTI. These are both Danish organizations. BKI is a coffee brand, actually, and DTI is something like Fraunhofer of Denmark. And they developed, or they had the idea to create an AI model which is recommending the ideal combination of certain coffee bean types if you would like to match a desired taste of the coffee. There are some metrics which are quantifying the taste of coffee, like the sour level of the coffee. So you specify these features of the taste, and then the model should recommend which kind of coffee beans should be blended together and roasted at a certain level to match these requirements of the taste. And we were involved in this project really to assess the model on certain aspects, for instance, about explainability, but also look into the entire development process and see if, let's say, gold standards and best practices were fulfilled during the development, and they got a report out of that, which helped a lot to improve the model. And this project actually won the Danish AI Award in the year 2023, if I recall correctly. But even we do not stop here. Once you have the model and hopefully done everything right at certain application, you have to think about auditing. We already spoke today about high-risk applications. But for instance, in quality control, which is our main core topic, this is also oftentimes an issue. You have a quality control system, and this needs to meet certain industry standards, like the measurement system assessment or the VDA 5 if you go to the automotive industry. So how does this auditing work in such industries? And we had a research project funded by the German government, which is called AI Qualify, really on the topic. Now you have a quality control system which is using AI components during the process of quality control. What do we do in this situation? This is not known to the standards, for instance, in the automotive industry. And we come up with a proposal, an idea how to support quality control system suppliers, for instance. The idea is that we especially address first-party and second-party audits, because this is very common in this industry. But we also think that our proposal, our AI quality system, would support third-party audits, which are also relevant for high-risk AI system applications. The core idea is about, as before, that you should take into account all the stages of the AI model development. Not only focus on the data and the model, but also the use case, the data selection, but later also on the deployment of the model. And this is actually in coincidence what agrees with the position of the TÜV Austria. There was a white paper of the TÜV Austria several years ago where they also recommended to take in consideration all the phases. So we also are well aligned with this one. And our key idea is, besides having this holistic view, that we support the persons, the people, by identifying and bundle all the criteria and metrics that are necessary in a common infrastructure, which we call an augmentation structure. You might know this also in the safety industry. This is quite well known, but we take it over into the quality control domain. And the third stage is, once you have this argumentation structure with all the criteria, we also provide means to assist the people in order to provide evidence to this argumentation structure. And this argumentation structure, if you're not familiar with it, it's not our development, but we just adapted it for our use. It's a tree-like structure where you have a main goal. You would like to prove that your AI system is able to fulfill, and then you start to break it down into sub-goals on a level that you reach that it's possible to prove or to provide evidence for individual sub-goals, and once you have all the sub-goals met, also the main goal is met. As you start from the bottom to provide evidence and provide a structured argument that your AI system is compliant with all the requirements of the use case. That's roughly what an argumentation structure is. And the problem with this kind of argumentation structure is, even though they are very, very well known in the safety domain, for instance, a big problem is they do not scale. So we are here again about scaling. Usually these structures are created manually, and for each use case you start over again and think about what is the best structure. And one of the core ideas in AI Qualify is to provide a basic argumentation structure automatically, just by providing some minor information about the use case that needs to be solved. And this information you need to provide, we call it ML dimensions. It's some kind of a clustering of the application. It has 3 dimensions. The first one is the machine learning task that needs to be solved, so whether it's a segmentation problem, and classification problem, and reinforcement learning problem. These are typical machine learning tasks. Then the paradigm that is applied, is it semi-supervised, supervised, unsupervised, so on and so forth. And then, of course, which kind of data is used, image, text, time series, combination of that. And once you have specified this, then this basic structure is created automatically. And from there on, the user still has the option to extend it by very specific, very use case specific additional requirements and criteria that need to be addressed. This again is an overview about the dimensions. That the key idea is really to support, to automate as far as possible the creation of this argumentation structure, because this was the problem in all the existing state-of-the-art solutions, especially in the safety domain. Here you see some examples. What is an ML task and paradigm and a data modality. One example here to give you an idea how this structure then looks like. This is a typical application. It's called an automatic optical inspection. So you use a camera or multiple cameras to do quality control on a specific item. Here we use something very simple, a simple washer, which has certain defects during the production, like bumps and dents or scratches. The challenge here is that the surface has a very high variance. You can see it a bit on the images, especially the smaller ones, depending on how the washer is oriented under the camera and the light. It appears more dark or light. Especially in scratches, this becomes then complicated to detect the scratches. And these AI systems, so there are 2 examples, 2 example criteria. that you need to provide argumentation that your AI system is working correctly, so that you get a reliable classification of all the 4 different defect types. And reliable means to a confidence level of maybe 99% and above. And you have a robust detection despite these high variation in the appearance of the washers. And what you see here is part of our argumentation structure, which is completely automatically generated, and this is only the data part of it. So the true structure is significantly larger. We've also parts for the model, for the deployment, and so on and so forth. So this is really only concerned about the data. Here's a zoom out about parts of which is addressing the variance aspects, and the color coding is like that everything which is in this grayish, bluish grayish color, this is a claim you can further subdivide. The green boxes are claims which are on a level that you really can provide evidence. The orange ones are you have to provide manual evidence like documentation or a checklist. And everything which is blue is evidence that is created automatically by the system. So the user is no longer involved. You can see in this assessment of the evidence, there is still some human involvement necessary. I think this will not go away, unfortunately. This is my last slide to give you a summary. So we are heavily involved in this dependable AI aspects by either providing really methods, tools for explainability, robustness, and uncertainty quantification, but we also support companies and other organizations to get the AI engineering process right from the beginning, and also support them and others by providing tools that make the auditing process a bit more easy for everybody. Thank you very much.
Yeah, thank you very much for this very interesting and hands-on talk, so which gives insight into this practical process of how to audit these products. Yeah, are there any questions from the audience? There's a question.
Hi, thank you for your talk. My question is about this rent method you've presented. And I was wondering about the scalability of this method. From the data sets I've seen on the slide, they aren't too challenging, I would say, for neural networks. What about, for instance, state-of-the-art image classification models? Does it also scale to that? Is it even useful for networks like this?
Yeah. You're right. On the slides, you have seen more or less toy data sets, which would be even unsolvable for the existing transformation methods. So our method is the first one which can at least address the larger toy problems, which the image classification example you mentioned, we showed that you can also transform CNNs with the common pooling aspects in this model. This is possible, but the scaling is not yet sufficient to address large-scale ResNet. Therefore, it would calculate hours to make these transformations. So for this specific large-scale models, we still have to work. Mathematically, it is possible, but computation-wise, it's still demanding. But for smaller models, like smaller, also recurrent neural networks, this also works, or smaller multi-layer perceptrons. Small means maybe 5 to 10 layers with some hundreds of neurons. This works in seconds. But for the larger ones, we have some ideas because still there is a lot of redundancy in the tree. So we provide nodes which are just not necessary, and this can be eliminated. So this is one of the ideas we have to speed up.
Okay, there's one more question before we go to lunch break.
Thank you very much for that interesting presentation. My name is Frank Blimmer. I'm an auditor for medical devices. Would you mind to go back to the last slide of your presentation?
You don't know. Okay.
Yeah, if you go down to the right, down there, does the model behave as required for all possible inputs?
Yep.
This is something, I mean, this drills it down to the end. You don't know the possible inputs, therefore you are always unable to answer that question. I mean, that's...
It is actually possible to answer all data. Let's take an example. If you have a image problem like this classification, an image is at the end nothing else than just a large matrix of numbers. So there is a limitation because it's all the pixel values, and under certain assumptions, you can provide mathematical proofs whether your model behaves satisfies certain requirements. The problem is, again, it does not scale. These problems of verification are NP-hard, so they do not scale well. But theoretically, it is possible to make a proof for all the inputs.
Theoretically, I fully agree, but let's move to the example we've seen, the cancer, the skin cancer thing.
Yeah.
I mean, we both know it's impossible that you predict all kinds of possible cancer pictures. Mm-hmm. And therefore, you say it's impossible, it stays impossible. Whatever you do, I mean, therefore, you can do or try what you want. You will always have to answer this question. No, you can't prove that. Sorry.
But what you can do is, and this is very common for these kind of robustness and verification procedures, that you consider a certain environment around, maybe you provide an example picture of this melanoma, and then you create a epsilon ball, actually an hyperball around that, and for these hyperballs you can provide a proof.
Would you agree that you should change that question? Does the model behave?
No.
Sorry.
No,
does it? Pardon?
No. This is the relevant question you need to answer, and it's about the research to provide means at some point in time to really provide an answer to this question.
Okay, I suggest to continue this discussion during lunch break. So we're now ready for lunch, and we will start for all the remote participants sharply at 1 p.m. So please join us again after lunchtime. Thank you again very much, Marco Huber, for this very technical, in-depth presentation. And after the lunch break, we will have our first panel, Trust Through Transparency. So, I'm very much looking forward to that one, and have a good lunch break.